Imagine standing on a world where the air weighs as much as the ocean a kilometer beneath the waves of Earth. The sky above you isn't blue, it's the color of rust, glowing faintly through clouds of concentrated sulfuric acid. The temperature is hot enough to melt lead. And the wind, far above your head, is sprinting around the planet at more than 200 miles per hour, fast enough to lap the entire world in just 4 Earth days. This is Venus. And believe it or not, it isn't even close to the most violent weather in our solar system. Earth's weather is, by cosmic standards, almost gentle. A Category 5 hurricane terrifies us, and rightly so. Tornadoes can tear apart neighborhoods. Blizzards can bury cities. But step out into the rest of the solar system, and you'll find storms that would make Earth's worst weather look like a polite afternoon breeze. There are winds that move faster than the speed of sound. There are storms that have been raging continuously since before the invention of the telescope. There are clouds that rain pure diamonds. And out there, on worlds we've barely begun to understand, weather operates by rules so alien that it forces us to reconsider what the word weather even means. Let's start with Venus, our supposedly Earth-like sister. Venus is the same size as our planet, formed from the same building blocks, sitting in the same neighborhood around the Sun. By all accounts, it should be a second home. Instead, it became a horror show. The surface temperature is around 465 degrees Celsius, that's 870 degrees Fahrenheit, hotter than Mercury, even though Venus is twice as far from the Sun. The reason is its atmosphere, a thick blanket of carbon dioxide, 90 times denser than Earth's, that traps heat with merciless efficiency. But what makes Venus genuinely strange isn't just the heat. It's the wind. High in the upper atmosphere, around 50 miles above the surface, the entire sky is moving. The clouds rotate around the planet so quickly that they complete a full lap every 4 Earth days. The planet itself, meanwhile, takes 243 Earth days to rotate once. So the atmosphere is moving roughly 60 times faster than the ground beneath it. Scientists call this superrotation, and we still don't fully understand what powers it. Some combination of solar heating and atmospheric tides is dumping enormous amounts of energy into those clouds, keeping them in perpetual motion. And then there's the rain. Yes, there's rain on Venus, but it isn't water. It's sulfuric acid, falling from clouds many kilometers thick. The droplets never reach the ground. They evaporate in the brutal heat of the lower atmosphere, only to condense again higher up. Venus has an eternal acid cycle, hidden behind perpetually overcast skies. Now travel outward. Past Earth, past Mars, until you reach the great gas giant. Jupiter is a planet that is almost entirely weather. It has no solid surface to anchor anything, just thousands of kilometers of swirling, churning atmosphere, racing in alternating belts of cloud, all driven by the heat the planet still radiates from its own ancient formation. And right there, in Jupiter's southern hemisphere, sits the most famous storm in the solar system, the Great Red Spot. The Great Red Spot is a single hurricane that has been raging for at least 350 years, possibly much longer. We've been watching it through telescopes since the 1600s. To this day, no one has seen it form, and no one knows exactly when it will dissipate. The storm is so large that, until recently, you could fit 2 or 3 Earths inside it side by side. It's been shrinking lately, which is a mystery in itself, but even now it's wider than our entire planet. Winds inside it howl at more than 400 miles per hour. And it has been rotating, unchecked, for 15 human generations. Then there's Saturn, and Saturn is where things get genuinely weird. At Saturn's North Pole, there's a storm shaped like a perfect hexagon. A 6-sided cloud pattern, 20,000 miles across, with each side roughly the diameter of Earth. The Voyager probes first spotted it in the 1980s, and Cassini watched it for over a decade. It's been there the entire time. We've reproduced something like it in laboratory experiments with rotating fluids, but the fact that nature simply produces a geometric shape that large, and holds it stable for decades, still feels uncanny. And the lightning on these gas giants is absolutely staggering. Jupiter produces lightning bolts thousands of times more powerful than anything Earth can muster. Saturn occasionally erupts in megastorms, vast white tempests that wrap themselves around the planet, lasting for months, before vanishing back into the cloud bands. But the truly extreme weather, the kind that bends imagination, lies further out. Beyond Saturn, beyond the asteroid-rich darkness, sit Uranus and Neptune, the ice giants. And on Neptune, scientists have measured the fastest winds in the entire solar system. Not by a small margin. Neptune's winds clock in at over 1,500 miles per hour. That's faster than the speed of sound on Earth. That's faster than most fighter jets can fly. And this is happening on a planet that receives about 1,000th of the sunlight Earth does. Without much energy input from the sun, Neptune should be sluggish, quiet. Instead, it's the windiest place we know. How can this be? Part of the answer lies in Neptune's internal heat. The planet radiates more energy than it absorbs from the sun, a leftover glow from its formation, slowly leaking out into space. This internal heat drives convection deep within the atmosphere, and that energy gets translated, somehow, into those terrifying winds at the cloud tops. There are dark spots on Neptune, massive storm systems the size of continents, that come and go on timescales of years. And now we come to the diamonds. Deep inside both Uranus and Neptune, the pressure becomes almost unimaginable. Tens of thousands of kilometers down, the methane in those atmospheres gets crushed so violently that its carbon atoms are squeezed out of their molecules and pressed together into something denser than coal, into diamond. Laboratory experiments here on Earth, using high-powered lasers to recreate those pressures for fractions of a second, have actually produced tiny diamonds from methane. Scientists believe that deep inside these planets, that process is happening constantly. Diamonds form, and then, because they're denser than the surrounding material, they sink. They fall. Slowly, through unimaginable depths, down toward the hot, rocky cores of these worlds. Diamond rain, falling forever, on a planet no human will ever walk. Closer to home, Mars produces its own brand of extreme weather. Mars has dust storms, and not the gentle dust devils you see in deserts on Earth. Every few Martian years, a regional storm grows and grows until it spans the entire planet. The entire surface vanishes from view, swallowed in a haze of fine red particles that linger for months. The 2018 global dust storm killed NASA's Opportunity rover by blocking sunlight from reaching its solar panels for too long. After 15 years of operation, it went silent in a planet-wide haze. Wind speeds in these storms aren't as fast as you'd expect, only about 60 miles per hour, but the atmosphere is so thin that the storms can't actually knock anything over. The danger isn't force, it's persistence. A dust storm on Mars is a slow, suffocating siege. And then there's Titan, Saturn's largest moon, a place where the very concept of weather takes on a strange new shape. Titan has rivers, lakes, and oceans. It has rain. It has clouds. It has weather cycles. But on Titan, none of this involves water. The temperature is so cold, around -180 degrees Celsius, that water is frozen as hard as rock. Instead, the weather on Titan is built around methane and ethane. It rains liquid methane out of methane clouds, into methane rivers, which empty into methane seas. Titan is the only other place in our solar system with a stable liquid cycle on its surface, and that liquid is hydrocarbon. Titan rains gasoline-like fluids under an orange sky. Step back, and a strange pattern emerges. Every world we visit operates by its own physics, its own chemistry, its own rules. The weather on Earth is just one solution among many to the problem of moving heat around a rotating sphere. And once you see it that way, the rest of the solar system stops looking like a collection of dead, sterile places, and starts looking like a vast laboratory of climates, each one running its own experiment, on timescales of millions or billions of years. What scientists find genuinely fascinating about all of this isn't the spectacle. It's what these extreme worlds teach us about the basic mechanics of atmospheres, including our own. Studying Venus is how we learned about the runaway greenhouse effect, the very phenomenon now reshaping Earth's climate. Studying the Great Red Spot teaches us about the persistence of large-scale vortices. Studying Neptune's improbable winds forces us to refine our models of how heat moves through a planetary atmosphere. Each alien storm is, in a way, a kind of mirror, showing us the alternate paths Earth's atmosphere could have taken, and could still take, given the right conditions. There's something almost humbling about that. The same physics that produces a thunderstorm above a Kansas wheat field is also producing a hurricane wider than Earth, on Jupiter, that's been raging since before the United States existed. The same chemistry that drives rain through our hydrologic cycle is, somewhere in the depths of Neptune, manufacturing